Hi champ. So last day we learned the basic chemistry of amino acid, and today we will learn the titration and how to calculate charge and different charge of different amino acid, okay, at different pH. That's most important because if you see that in cellular component the endosome has different pH, the lysosome has different pH, nucleus has different pH. So this charge calculation and uh, that will help you to visualize what can be the situation inside nucleus, endosome, and all these things. Side by side, I can ensure you that here at least you can get plus 1 to 2 marks because that's very important concept. Okay, for IIT JAM and GAT-B and CUTPG for all these three exams. It's very important. Now, last day we learned about few concept, that's the basic amino acid concept, and we classify amino acid on 4 class. So I am writing the amino acid name GAVLIFMWP, that's one set, right? And then CSTYNQ, that another set, and finally HRK, that another set, and DE, that another set. All the amino acid here is represented with single letter codon, single letter amino acid, right? So G means glycine, A means alanine. I think you know that. Like V means valine. Okay. Now that we classified under non-polar, uncharged R group. You remember that one we classified under polar charged, right? That one we classified under positively charged amino acid. That we classified under negatively charged. That's also polar. So that molecule, like histidine, arginine, lysine, the side chain is also polar, but this is positively charged. This is negatively charged. You can also write polar because always anyway there is COO minus, there is extra NH 3 plus. Okay, now today we will see their titration. So before going to titration, I just want to remember you one equation: Henderson-Hasselbalch equation, HH. Henderson-Hasselbalch equation. Okay, so this is class 12 concept. In generally what happens, suppose there is one acid Ha. Now this acid is dissociating. Okay, this will dissociate into H plus and A minus, right? So I am writing here Ka, or so if you write Ka here, what you will write? H plus, A minus, and H. Now if I tell you to take log of both sides, that will be log base 10 Ka into log the base is 10, and then H plus, A minus by Ha, right? And from here what you will get? Log base 10 Ka into log H plus log A minus by Ha, right? This is the basic logarithmic rule. Okay, so from here you can get it that you can just do side exchange. So minus log H plus equals to minus log Ka plus log A minus by Ha. Okay, that it means minus log H plus, that's the pH, and minus log Ka, that is the pKa, equals to log A minus by Ha, right? Now if you remember the acid base concept, right, there is some, suppose there is CH3 COOH, this is acid. What will be its conjugate base? CH3 COO minus. So if I tell it acid, then it should be conjugate base. Okay, conjugate base. Now similarly you can do Ha, right? H minus, this is the sorry, A minus, this is the conjugate base. So we can write that equation similarly. pH equals to pKa plus log, then conjugate base by acid, right? We can also write in same way, or we can write A minus by Ha, both of these things. Now suppose at some pH both of this concentration, that is Ha equals to A minus at some pH, now at that situation what it will be? pH equals to pKa plus log, as these two are same, so the ratio will be 1, log 1 equals to 0, so pH equals to pKa. So pH equals to pKa at, so pK is nothing but the pH at which the ratio of conjugate base and acid is 1, that we will call it as pK. Okay, now as amino acid has two ionizable group CHR generally, so we have to figure it out the titration curve for this 20 amino acid. Okay, so generally for 20 amino acid there are only three kind of titration. If you see here, so these all are uncharged, so generally for uncharged we consider one titration curve, and for positively charged we consider another titration curve, negatively charged we consider another titration curve. Though the here the catch is for polar group like SH, okay, for OH, this side group also shows some kind of pK. So you have to you have to aware of this thing, that some in some question they can mention you the pK of this, but it's very rare. Okay, generally we'll categorize into 1, 2 and 3 different titration curve. Okay, now first I will do with alanine. NH3 plus CH COOH, write it like that, and then here it is CH3. So this is at very low pH, right? Now if you add, okay, sorry, okay, I should not mention it like that. Okay, so now if you add OH, right? If you add OH here, then which of the molecule like carboxyl or amine will release proton first? Of course the carboxyl. Now what will happen? H3N positive, CH, COO minus and CH3. Now again if you add OH minus hydroxyl group, some bases, what will happen? Then that proton will that amine group will release proton. Now what will happen? H2N CH COO minus CH3. So at that condition the charge is called +1, because you can see +1 charge is there. Here the charge is 0, here the charge is -1. Okay, so as soon as you are increasing the hydroxyl, at that time the amino acid molecule will release one by one proton. So the first proton, please note that first proton or H plus will be released by COOH group, and then NH3 plus will release proton, release H plus. So COOH generally release proton by pH around 2 ± 0.5, and NH3 it's 8.5 plus minus zero point 0.5 or 9 plus minus zero point 0.5 you can say. So suppose this is at pH 2, pH equivalent to 2 and pH here almost 9. Now if I tell you find the isoelectric point, find isoelectric point. Trust me or not, in exam only simple questions are asked and we used to do mistake in the simple question only. So here what will happen, isoelectric point means at that point the amino acid is carrying zero charge, one thing, or you can say it's not moving to cathode, not moving to anode, another thing. Third thing, you can say the positive charge amino acid and the negative charge amino acid, their quantity is same. That means alanine plus equals to alanine minus. That means the total charge of the solution is 0. Total charge 0 at pi, isoelectric pH. So pi is the pH at which the total charge of a solution is 0. That means the amount of positive charge amino acid equals to the amount of negatively charged amino acid. And how you can calculate the pi? So pi is calculated as, so here I am writing it pk1 and I am writing it here pk2. Pi is always the calculated between plus 1 and minus 1. Remember, plus 1 and minus 1. So what it will be, pk1 plus pk2 divided by 2. That means 2 plus 9 divided by 2. That will be almost 5.5 or something. It's a hypothetical condition. Okay, so like that there are different other amino acids and we have to check for different kind of amino acid. If I say you calculate for valine or something, you can do it by your own, just only altering the side group because the side group is same, right? So here you have to remember the pi equals to the pk1 plus pk2 by 2, and pk1 is that condition from where plus 1 to 0 and pk2 is 0 to minus 1. Just remember that thing only. Okay, now if we want to do for let's assume aspartate. Okay, so first write down the structure of aspartate at maximum protonated condition. If you want to learn it, just trust me, just write down first the maximum protonated condition. So CH, COOH and CH2, COOH. Right? So here the aspartate is positively charged. Now if you increase OH minus, then what will happen? Then NH3, then CH, COO minus, CH2, COOH. That's why you should practice and remember that carboxyl group that is attached to the alpha carbon, it will release proton first. So that will release proton first. So as it's releasing the proton first, now if I am writing it at pk1 at pk2, so this pk1 is around 2, now pk2 is around 3.6. now what will happen? H3n plus CH, COO minus, CH2, COO minus. Here the charge is 0, here the charge is minus 1. Now if you again add hydroxyl group, some base, then what will happen? That amine group, that will also release proton. Okay, that will now release proton. So this is called as pk3. Now what is happening? H2n, CH, COO minus, CH2, COO minus. This is minus 2 charge. So here minus 2 maximum charge you can gain, that is minus 2. Okay, now if I tell you what is the pi, find the pi. So this pk is almost 9. Remember pi is always the thing of plus 1 and minus 1. So what is plus 1 and minus 1? That is pK1 plus pK2 divided by 2. That means 2 plus 3.6 divided by 2, almost 5.6 by 2, 2.8, hypothetical, right? And then so for aspartate, you have, for any amino acid, please calculate from the maximum protonated condition. That means plus 1, then 0, then minus 1, then minus 2. Similarly, if we do for, let's see, lysine, okay, K. Lysine, what happened? Maximum protonated charge H3N, CH, COOH, now CH2 whole 4, and that is NH3. That's why I always tell people to remember the structure. If you remember the structure, it's very easy to do this calculation, right? So here the charge is plus 2. Now if you add some hydroxyl group, what happen? That carboxyl group will release proton first. NH3 plus CH, COO minus CH2 whole 4, and here NH3 positive. Here the charge is plus 1. Now again you add hydroxyl group. Now what will happen? You have to remember that time, because the side chain pKi is almost 10.5 plus minus 0.5, the side chain or side chain amine. So suppose here this is pK1, this pK1 is almost 2, this is pK2, this pK2 is almost 9. At 9, that will release proton. That's the condition. So CH2 whole 4, NH3 plus. So at that time the charge is 0. Now again if you add hydroxyl group, what will happen? H2N, CH, COO minus, CH2 whole 4, and NH2. At that time the charge is minus 1, right? So first this carboxyl group is releasing proton. Second, the amine, that is attached to the alpha carbon, that is releasing proton. The third thing, the side chain is releasing proton. Okay, so now if you calculate, so that's almost 10.5 something. If you calculate the pi here, it will be pK2 plus pK3. I am writing it here at pK3 divided by 2. That means 9 plus 10.5 divided by 2. That means 19.5 by 2. That's around 9.75. Okay. So the basic thing is that you should remember the pK of side chain. I am writing it for you, but okay. So in generally, alpha carbon related COOH, that is directly linked to C alpha. Its pK. So this is pK value. Its pK is around 2. Now C alpha direct to NH3 plus. It's related to 9. Now the side chain, I will write for side chain. For aspartate, D, aspartate. For aspartate, COOH, side chain, of course, that's around 3.6. For glutamate, that is E, the side chain, COOH, that's around 4.2. For histidine, H, that's the NH3 plus condition, or you can say because in histidine it is in imidazole format, so there is something like that. Okay, here NH plus. Okay, so in that situation, in case of histidine, it is near around 6 plus minus 0.5. For lysine, it's also the side chain NH3 positive epsilon condition, that's also 10.5. For arginine, that is, yeah, for arginine, the NH to guanidino group, that is 12.5 plus minus 0.5 error. So if you remember that basic things, then you can easily solve the titration curve and the titration plot and the charge. Now if I tell you to draw the titration plot for alanine, okay, alanine, just go back here, right? So at 5.5 there is similar amount of positive and negative charge, right? Now here in that direction it's written as pH. In y direction, in x direction I am writing OH minus. It's not exactly perfect, anyway I'm trying to do it. Okay, now there are different points. There is one point here, one point here, and another point here. I should not do that. Okay. Okay. One point is here. Now what does this point signify? That point signifies, so what's happening from basically alanine plus. Now from alanine plus you are going to alanine 0. From alanine 0 you are going to alanine minus 1. That means here this is pK1, this is pK2. At that situation the alanine plus equals to alanine 0. Remember I told you that pH equals to pKa when HA equals to A minus, right? Conjugate base pair. So here as the alanine plus and alanine 0, there's one proton difference, that's why they are conjugate acid base pair. Here the alanine plus equals to alanine minus 1, and here alanine minus 1 equals to alanine 0. Why it's like that? You can do it from Henderson-Hasselbalch equation. pH equals to pK. So suppose pK plus log, okay, log alanine 0 and alanine plus, that at that condition if this two ratio is 1, that will be what, then I can say pH equals to pK. So that is called pK1 and that is called pK2, and that point is called pi. At pi, so the positive charge amino acid and negative charge amino acid is similar, is in same quantity, sorry, is in same quantity, okay. And you can do similarly for glutamate, aspartate, okay, but you have to be careful about deciding the point at what point. So suppose that point comes around 2, that point comes around 6, that point comes around 9. So at 6 this is the pi, at 2 that's the pk1, at 9 that's the pk2, right? This is the titration plot of alanine. Okay, and in between here, if I tell you what is happening here, here alanine plus is more than alanine 0, because it's slightly just leaving the proton. I hope you guess it, right? It's slightly leaving the proton. And if I tell you what is happening here, here the thing is that alanine plus is less than alanine 0. Now maximum of the alanine released the carboxyl group proton, right? Here also if I tell you, there is also two things applicable. Here is one condition and uh, here is another condition. Here the condition is the alanine 0 is more than alanine minus 1. Here alanine 0 is less than alanine minus 1. It's quite complicated, but if you practice it and if you understand it, then it's really easy. The thing is that if you write from the maximum protonated state and then you are reducing one by one proton, then you can imagine. So first there are a lot of proton, then few amino acid release proton, few amino acids still in positive condition. Then at a certain point, both positive charge amino acid, negative charge amino acid same. After that, if you again increase the hydroxyl group, at that time what's happening? At that time, maximum of the amino acids are in negatively charged condition. So you have a little bit imagine, and along with that you have a little bit calculate. Okay. Now we will do charge calculation. Charge calculation. Okay. So for charge calculation, I am giving you few tasks. Suppose my name is Manas. Manas. I am telling you calculate the charge of the peptide. Okay. Of course, that's a peptide. So different amino, the first different letter is indicating different amino acid. Right. Suppose M means methionine, A means alanine, N means glutamine, A means alanine, again S means serine. Right. So at that time, if I tell you calculate charge of the peptide at pH, first let's assume at pH 3, then what will happen? At pH 3 you have to first see, so for step 1, observe whether there is any charged amino acid or not. Charged amino acid or not. Step 2, what you have to do? Write down the amino group in that format and then MANAS and then COOH in that format. Okay. Now you are told just write down in that format, then step 3, what you have to do, you have to see the pH 3 and you can remember that the carboxyl group that is attached to the alpha carbon, so alpha carbon of serine. Okay, because in between they form peptide bond. I will tell you what is peptide bond maybe in tomorrow's class. Okay, so at that condition, consider these MNAs as a single amino acid. Okay, just a block like that, single amino acid. This is alpha. Okay, and this is the serine. Now this is NH3 plus and this is COOH minus. This is COO minus because we know the at pH near around 2 the alpha carbon COOH protonated, deprotonated, right? Now you can calculate now the basic charge is +1 -1, that is 0. You can try few things and suppose charge amino acid. Okay, H S A L I K and D and A for this amino acid. What you have to see, few amino acids are charged here. First thing, the histidine charged. Generally, the lysine and aspartate. It's possible. Now it depends on at what pH. Suppose at pH, I am telling you at pH 8, what will happen? So step 1, first write down the you have identified the possibly charged amino acid. Step 2, we have to write down the NH3 positive and then H S A L I K D A and then COOH. But as the pH is 8, then what will happen? The COOH will release one proton and become COO minus. Now the charge from here is -1, charge from here is +1. Write down the charge. And we know the histidine side group. Okay, the histidine side group also release proton at pH around histidine around pH 6 to 6.5, and there is one thing called lysine 10.5, and for aspartate also released by 3.6. So now this will show also -1, right? Because it already pH already 8, and histidine it will already released one proton, now it's zero condition. Okay, the side chain already released the proton, now it's in zero condition. Now this is already in +1 condition. Now calculate the charge. +1 -1 0, +1 -1 0, that means +2 -2, that is 0. So net charge at pH 8 equals to 0. Similarly, if I tell you at pH 5, then what you have to do? All the things, suppose NH3, this will release plus, this will be like that +1. Histidine, right now it has not released the proton, so you have to write +1. Serine, alanine, and leucine, and all these things are uh, non-polar and uncharged. And after that the lysine comes again +1, and for aspartate again -1, for COOH again -1. That means +3 -2. At pH 5, net charge equals to +3 -2, that is +1. So like that you can play with different amino acid and different peptide. Okay, so I hope that you get the concept, and you can practice some more thing. Suppose your name, your family name, and few peptide. So I'm giving you, suppose DLKRMTA at pH 9, at pH 3, at pH 13. Then PENSTAND at pH 6. Then LATTRKS at pH 8. You can do these things. If you are facing any issue, we can discuss it in next class. And along with that, tomorrow we will start secondary structure and amide bond formation, and Ramachandran plot. Okay, keep enjoying. Okay, see you tomorrow.